So today we'll be talking about exponential growth models. Basically, when we talk about exponential growth, it basically is representing a situation where there's a percentage growth during a certain period of time. Some sample examples are growth, prices, increase, and compound interest. Our basic equation is y is equal to a b to the x. Now, for the growth situation, b will be bigger than 1. Now, the a value is what we call the start value. The b value represents either the decrease or the increase that we're looking at. And we call a decrease decay and an increase calling it growth. When we have decay, our b value is between 0 and 1. And for growth, our b value is greater than 1. Now, there are three types of equations we're going to use. We're going to have one, y is equal to a b to the x. When we look at this equation, y is equal to 2, bracket 1/3 to the x. This means the starting value is 2, and the 1/3 means every number gets cut by a third every single time we move from left to right. The second type of equation is y is equal to a 1 plus r raised to the x, where r is the rate as a percentage. Now, the other equation is y is equal to 1 minus r raised to the x. 1 represents the increase, i.e. growth. In this case, the total of what's in the bracket ends up being bigger than 1, so therefore it grows. And the second one, if we have 1 minus whatever percent as our decay, is representing a decrease. So for example, if I have y is equal to 500 bracket 1 plus 0.05 to the x, this means this equation is an increasing exponent. But if you notice, I could write that as b is equal to 1.05, which means it's increasing. Okay? So anytime I give you a percentage, you use these two equations in order to use either increase or decrease. Increase means we're adding, decrease means we're subtracting the r value. So the last equation is y is equal to a b to the x over d. The d value in this case represents the time it takes to either double or triple or quadruple or get chopped in a third. Right? Now, you'll see several questions like this in growth or decay. So for an example, I'll give you this equation. We've got y is equal to, let's go 500, and we've got 2 raised to the x over 24. The 24 underneath in the exponent part basically will tell us something interesting. Now remember, the first part is our start, the 500. The 2 tells me that it doubles, and the 24 tells me that it only doubles every 24 hours. So you'll see a problem like this when we do more in-depth calculations using doubling time. Okay. Now let's take a look at the next problem. Now, the value of a house increases by about 3% each year. The value is $125,000 for the house, and can be modeled by the equation v is equal to 125 plus 1.03 raised to the x. So this equation is very similar to equation number 2 that we had up here, where 3% is represented as 0.03. And we use that in our equation. So we get y is equal to a 1 plus 0.03, which turns into something raised to the x. Now the a value is still 125 because that's our starting value for the house. And our b value is 1.03. And we know that anything bigger than 1 is a growing exponential. So when we sketch the graph of the situation, you'll have an intercept of, I think, 125,000 since that represents the start. Okay, and because it's increasing, it starts low and ends high with a very swooping curve. Okay, and then we can indicate that that's our basic graph here. So now what we're going to do is we're going to take a look at the basic question when we ask for how much will this thing be worth after 5 years. The key idea is when we know that x is represented by years, we're going to sub x is equal to 5 into the equation. So we're going to get v is equal to 125,000 bracket 1.03 raised to the x. In this case it's 5, and we just punch that directly into our equation and we get 144,909.26, and now we state as our final answer, therefore the value of the house is 144,906. Now just make note of that little bubble that we have on the side there. When you're punching this into the calculator, you punch it in exactly as you see here, and when you do so, your calculator will handle the calculation properly. Now, what's the value after 10 years? You try that, pause the video, and you should see this. Easy calculations. And you'll notice that the only thing we've changed is the 10. We've chosen that x is 10 because it's 10 years from now. And now we'll move on to the next set of problems. So in this case, we have a bacteria colony that's described by this problem. Now you'll notice the 5 in front of the 2 basically represents the initial amount of bacteria. How many bacteria will be present after 4 hours? So we're going to do exactly the same pattern as before. We're going to sub x is equal to 4 into our equation, but this time what you're going to do is you're going to simplify the exponential that says 4 over 4 and change it to 1, calculate, and then you'll get your final answer being 10. And you'll say, therefore, the number of bacteria after 4 hours are 10. All right? Now, the key idea to solve these problems is you simplify the exponent as much as you can. Sometimes you can't, sometimes you have to punch the number directly in. Now, this next one asks you, how many bacteria will be present after 20 hours? So now what you're going to do is you're going to just sub x as 20. And because 20 divided by 4 gives us 5, we just punch it into the equation. We simplify the power first, and then we calculate the final example, the final calculation, by following the rules that we did before. So we end up with 160. So therefore you say, therefore there's 160 bacteria after 20 hours. And that's it. Now your homework is what you see on this page. I do believe it's page 401. No, 391 and 401. 391, 6 and 7, 401, 1 and 2, and there's no graphs to be done.